Swayam Prabha. Digital India. Educated India.
Now, in continuation of norm and distance between the 2 points of the vectors of these vector spaces associated, now let us go to discuss the orthonormal basis. Now, based on that orthonormal basis, consider n-dimensional vector space V and the basis B1, B2 and so on Bn of V. If the inner product Bi comma Bj is equal to 0, if I not equal to j, and if I equal to I and j are equal, that is I equal to I equal to j, then Bi comma Bi of inner product equal to 1. So, that is the meaning of orthonormal basis. So, for all I comma j varies from 1 to n, then the basis is called an orthonormal basis denoted by ONB, orthonormal basis. If only the condition 3.33 is satisfied, then the basis is called it as orthonormal basis. Note that the second condition implies every basis vector has a length of norm 1. So, that is the definition of orthonormal basis. Now, based on this orthonormal basis, shall we go to discuss one example taking into consideration of canonical standard basis for a Euclidean vector space R power n is an orthonormal basis where the inner product is the dot product of the vectors. If R square equal to B1 equal to 1 by root 2 of 1 comma 1, it means if you have a eigenvalue and eigenvector of the given matrices, then the orthonormal is eigenvector is 1 comma 1, then what you have to do is 1 divided by root of 1 square plus 1 square, we have to do that. Similarly, for B2 this is B1 and we have a 1 by root 2 and then B2 having what 1 by root of 1 square plus minus 1 the whole square comma minus 1 by root of 2. So, this can be generated with the help of what orthogonal and orthonormal as well as eigenvalue eigenvector corresponding orthonormal basis can be generated. Now, two vectors B1 and B2 are orthonormal if and only if B1 transpose B2 should be 0 and you take a norm of B1, definitely 1 will come. Similarly, norm B2 you take it 1 will come because norm is root of 1 by root 2 the whole square. Norm of B1 is nothing but root of 1 by root 2 the whole square plus 1 by root 2 the whole square, which is equal to root of 1 by 2 plus 1 by 2 equal to 1, which is equal to 1. So, it satisfies that orthonormal basis of two vectors. Now, keep it in mind this, let us go to the next ideas, right, that is orthogonal complement. Now, we are going to discuss orthogonal complement. Consider a d-dimensional vector space V and m-dimensional subspace U which is subset of V, then its orthogonal complement is U perpendicular is d minus m dimensional subspace of V and contains all vectors in V that are orthogonal to every vector in U. Further, u intersection u transpose or u perpendicular equal to 0, that is called as u intersection u complement equal to 0. So, intersection is empty. So, any vector x in V can be uniquely decomposed into x equal to summation m equal to 1 to m lambda m bn plus summation j equal to 1 to d minus m psi j bj complement, and lambda m and psi j r belongs to R, where the vectors b1, b2 and so on, bm is the basis of u, and b1 complement and so on, b suffix d minus m complement is the basis of u complement. So, this is the meaning of the plane u in a 3-dimensional vector space can be described by its normal vector which spans its orthogonal and orthogonal complement u perpendicular. So, this is the way the red arrow indicate that they are mutually perpendicular to one another, and then we can easily identify which one is a orthogonal, which one is a complement and so on. Next we have to start with the inner product of function. An inner product of two functions u such that r to r and v such that r to r can be defined as what a definite integral. Inner product u comma v is equal to integral a to b u of x into v of x dx. So, this is the notation we can do with the help of inner product. Rather, inner product of u comma v corresponding element you have to take it, simply add it, that is also inner product will come. So, for lower and upper limits of a comma b is less than infinity, and as with our usual inner product we can define the norms and orthogonality by looking at the inner product, and the equation 3.37 evaluates to 0 the function u and v are orthogonal. Now, we have to discuss an example, inner product of functions. If we choose u equal to sin x and v equal to cos x, and then f of x equal to u of x into v of x is shown in the figure of what 3.37 of the equation, shown in the figure of 3.8, that is discussing the sinusoidal wave, and then it generate with what one domain to the codomain when it is represented in terms of the cos x, and then multiply them, and we have a what a signal comes like that, and this means the inner product of the function they are designing, and take the limit a equal to minus pi and b equal to pi of this product, evaluates the value becomes 0 because one is orthogonal to other, therefore sin and cos are orthogonal function. Also note that it also holds that the collection of function 1 cos x, cos 2x and cos 3x is orthogonal if we integrate from minus pi to pi, that is any pair of the functions are orthogonal to each other. The collection of the function in 3.38 spans a large subspace of the function that are even and periodic on minus pi to pi. So, periodic in the sense that you have to take a curve 0 to 2 pi, and then within 2 pi the remain as it is after expand 2 pi to 4 pi. So, therefore, every 2 pi the curve remains same, then the period is what 2 pi. So, like that according to the picture we have to find out the period, and the formula is f of x plus lambda equal to f of x, where lambda is a period, like that you have to identify. Now, even the function is a periodic, and a projection function onto the subspace is the fundamental idea behind the Fourier series. So, if you want to expand the Fourier series of the function, ultimately you know what is the periodic function and what is the bounds, what is the upper bound, lower bound, and then whether it is even or odd, like that you have to check it out all these things, and then we can expand f of x equal to a naught by 2 plus summation n equal to 1 to infinity a n cos n x plus b n sin n x, where a naught, a n, b n or Euler function can generate in terms of the Fourier series. Now we have a orthogonal projection. This picture shows that orthogonal projection of a two-dimensional data set, blue dots onto the one-dimensional subspace straight line, and if you have a orange and then mixing together, they are orthogonal to one another. So this is the meaning of orthogonal projection. Next we have to discuss projection. So if V be a vector space, let V be a vector space and U is a subset of V, a subspace of V. So a linear map pi such that V to U is called a projection if pi square can be expressed pi into pi equal to pi. So this is the meaning of projection. Now projection onto one-dimensional subspaces. Assume we are given a line, one-dimensional subspace through the origin with the basis vector b in r power n. The line is a one-dimensional subspace of U is subset of r power n spanned by b. When we project x in r power n onto U, we seek the vector pi suffix u of x belongs to U, that is the closest to x. Using geometric arguments, let us consider the characteristic sum properties of the projection pi u of x as shown in the figure A 3.10 of figure A serves as the illustration. Now we have a orthogonal projection, then projection x in r square onto subspace U with a basis vector b. So the orange arrow represent we have a project on this, and then if you have a x in r square onto the subspace of U is a basis vector b. Now for the projection of the two-dimensional vector space, the norm of x equal to 1, therefore we have to make a arc of this arrow, and then at that point of this contact, and we can make a right angle triangle, and omega represent cos, and this perpendicular represent sin omega, so that one is orthogonal to another. Therefore by projection of two-dimensional vector space x with the norm of x equal to 1 onto a one-dimensional subspace spanned by b. So the projection pi u of x is closest to x, where closest implies that the distance norm x minus pi u of x is minimal. It follows that the segment pi u of x minus x from pi u of x to x is orthogonal to U. So therefore the basis vector b of the U, the orthogonality condition yields pi u of x minus x comma b equal to 0, since angles between the vectors are defined through the inner product. So the projection pi u of x onto U must be an element of U, and therefore a multiple of the basis vector b that spans U. Hence pi u of x equal to lambda b for some lambda in R. So in the following three steps we determine the coordinate lambda, the projection pi u of x belongs to U, and the projection matrix p pi that maps any x in R power n onto U. Number 1, finding the coordinate lambda, the orthogonality condition yields inner product x minus pi u of x comma b, which is equal to 0 if and only if pi u of x map equal to lambda b, then x minus lambda b comma b, which is equal to 0. Now from 3.39 you can split it into two inner product, that is exploit the bilinearity of the inner product and arrived at from this x minus b one separated and lambda b comma b separated, lambda is constant, take it outside. So, this will come like this equal to 0. If and only if from this you have to bring other side. So, lambda equal to x comma b by b comma b. Now, since it is a symmetry, inner product x comma b equal to b comma x, and then inner product b comma b is norm b square. So, in the last step we exploited the fact that the inner products are symmetric. So, if you choose the inner product of two elements to be the dot product, we obtain lambda is equal to this 3.40 becomes b complement of x divided by b complement into b. So, that is the b complement into b is nothing but norm b square. Therefore, that is a representation of equation 3.41. So, if norm b equal to 1, then the coordinate lambda of the projection is given by btx, b complement x. Number 2, finding the projection point phi u of x in u. Since phi u of x equal to lambda b, we immediately obtain from 3.40 that phi u of x equal to lambda b, which is equal to inner product x comma b by norm b square into b. So, b transpose x by norm b square into b, that is equation 3.42, where the last equality holds for the dot product only. So, we can also compute the length of pi u of x by means of definition. So, we have norm of pi u of x is equal to norm of lambda b, which is equal to mod lambda into norm b. So, hence our projection is of length modulus of lambda times the length of b. So, this also adds the intuition that lambda is a coordinate of pi u of x with respect to the basis vector b that spans our one dimensional subspace u. So, if we use the dot product as the inner product, we get pi u of x is equal to norm of pi u of x is equal to that is taken into account of 3.42, that is equivalent to modulus of b transpose x by norm b square into norm of b. Now, what we can infer according to equation 3.25, we can write this expression as norm of cos omega into norm x into norm b by norm b square. Therefore, everything norm b square will get cancelled, therefore, cos omega norm x. So, that is the meaning of if you use the dot product, then the resultant will be comes like this. Here omega is an angle between x and b. This equation should be familiar from trigonometry. So, if norm x equal to 1, then x lies on the unit circle. So, it follows that the projection onto the horizontal axis spanned by b is exactly cos omega, and the length of the corresponding vector pi u of x equal to modulus of cos omega. So, as an illustration given in the figure 3.1b, the third point says that finding the projection of the matrix P pi, we know that the projection is a linear mapping, see the definition. Therefore, there exists a projection matrix P pi such that pi u of x equal to P pi x with the dot product as a inner product. Therefore, pi u of x is equal to lambda b, which is equal to b lambda. Now, we can substitute b into lambda is equal to b transpose x by norm b square, and then b into b conjugate, and b into b conjugate into x by norm b square. So, the resultant of this one is P pi is equal to b conjugate by norm b square. So, here b conjugate is a symmetric matrix and the rank is 1, and norm of b is nothing but inner product of b comma b, which is a scalar. So, these are all the inference we can learn from the projection, orthogonal and orthonormal. Now, the projection matrix P pi projects any vector x in r power n onto the line through the origin with the direction b, equivalently the subspace U spanned by B. So, note the projection pi u of x in r power n is still an n dimensional vector and not a scalar. However, we no longer require n coordinate to represent the projection, but only a single one if we want to express it with respect to the basis vector B that spans the subspace U, that is such that the lambda. Now, we have a orthogonal projection. So, the orthogonal projection onto a two dimensional subspace is represent the figure and we have a two bases B1 and B2, right, and then based on the B1 and B2 basis we have a projection pi u of x which belongs to what three dimensional effect of x, this one, and then that x belongs to three dimensional effect and can be expressed as a linear combination of both the basis B1 and B2, and we have a displaced with x minus of pi u of x, and this seems to be that perpendicular to one another, call it as orthogonal to both B1 and B2. So, this way we can represent the pictorial representation of orthogonal projection. So, for one dimensional we have a only line, for two dimensional one is perpendicular to another, for three dimensional you see the cuboid, right. So, we have a three dimensional effect of the step 3. So, it means they are mutually orthogonal vector. So, one is trivial case, for two one is perpendicular to another, they are orthogonal to one another. For 3, x is perpendicular to y is perpendicular to z, and z is perpendicular to x, and vice versa, and all these three are mutually perpendicular to one another. Therefore, they are mutually orthogonal vectors. Now, let us go with one basic ideas. Two vectors x and y in a complex inner product vector space are orthogonal if and only if norm of alpha plus beta square is equal to norm of alpha x square plus norm of beta y square. So, let x and y be orthogonal, it means the inner product of x comma y equal to 0. Now, norm of alpha x plus beta y square is equal to inner product alpha x plus beta y comma alpha x plus beta y. Now, we can split it into 4 terms. First alpha x into alpha x, and then alpha x into beta y into alpha x, and beta y into beta y. So, we have a 4 term alpha x beta y comma alpha x, beta y inner product. Now, from the first one alpha, both having alpha, take it outside, therefore norm alpha x square. For second one, all these two scalar are not equal, therefore keep as it is. And third one, compare with the second, they are conjugate to one another, therefore alpha x comma beta y whole conjugate you take it. For fourth one, both are same, therefore norm beta y square. So, for first one norm alpha x square, for fourth one norm beta y square, and you have a z is a complex number, and then z bar equal to x minus iy, then if you add z plus z bar, then we have a 2x, therefore z plus z bar equal to 2 into real part of z. So, keep it in this mind, therefore, we can write second and third, we have 2 into real part of alpha x comma beta y will come. Now, keep it in mind this, go to the next step, norm of alpha x square plus norm of beta y square plus 2 times of real part of, you take alpha outside and beta of the second term, it will go to the beta bar of x comma y, therefore, norm alpha x square plus norm beta y square, since they are orthogonal, therefore, inner product x comma y equal to 0, therefore, this part will be vanishes. So, that is the meaning of what the norm of alpha x plus beta y square can be expressed norm alpha x square plus norm beta y square. So, conversely, given norm of alpha x plus beta y square equal to norm alpha x square plus norm beta y square, Hence, from the equation 1 we can get norm of alpha x square plus norm of beta y square plus 2 into real part of alpha beta bar into x comma y, which is equal to norm alpha x square plus norm beta y square. Therefore, 2 into real part of alpha beta bar of x comma y equal to 0. This implies inner product x comma y equal to 0. They are orthogonal to one another. So, if they are orthogonal to one another, we can express this expression. This expression is whole, it means they are orthogonal to one another. So, that is the inference we have learned from this theorem or example. Next example, if x comma y is an orthonormal set in inner product vector space, then find out the distance between x and y. So, what you have to do, since x comma y is orthonormal, therefore, norm of x square is inner product x comma x equal to 1, norm of y square is inner product y comma y equal to 1. This implies what? Inner product x comma y equal to 0. So, by the definition between x and y, norm of x minus y equal to norm of x minus y square equal to inner product of x minus y comma x minus y. Now, split it into 4 terms. So, x comma x, x comma minus y and minus y comma x and y comma minus y comma minus y. Now, in the second part we have a minus, take it outside. Therefore, x comma x minus of x comma y, and for the third one, that is first part is minus 1 and then take it outside, minus will come y comma x, and the last term both are minus, minus into minus plus, therefore, y comma y will come. Now, you know, if they are same, then the value is 1, they are different, the value is 0. Therefore, what? The value becomes 1 minus 0 plus 1 equal to 2. So, it means norm of x minus y the whole square equal to 2, taking square root on both sides, therefore, norm of x minus y equal to root 2. So, this way we can say that if x and y are orthogonal set of the inner product, then the distance between them are orthogonal, and then we get the value of what? This norm of x minus y. Next example, if x and y are the vectors in a real number inner product space, if norm x equal to norm y, then x minus y and x plus y are orthogonal. So, interpret the result geometrically. Now, the solution is, let x and y be any two vectors in a real inner product vector space such that norm x equal to norm y. Now, let us start with the norm x plus y comma x minus y. Now, what happened? We have to split it into 4 terms. For first one x comma x, second term x comma minus y, and third term y comma x, and then the last term plus of y comma minus y. Now, you take it outside, so that y comma x will come, minus of x comma y will come, and y will come. So, for first term norm x square and last term norm y square, in between x comma y minus x comma y, both are what? Equal to one another. Therefore, these two become 0, and therefore, first term norm x square, last term norm y square, and then the resultant is norm x square minus norm y square equal to 0, means this is the condition of what? The two vectors are in the real inner product space, they are orthogonal, corresponding representation x plus y and x minus y are orthogonal. Next example, if M1, M2 and M1 are pairwise orthogonal subspaces in inner product vector space V, and alpha equal to alpha 1 plus alpha 2 and so on alpha n be the summation of n vectors, where alpha I in Mi, where I varies from 1 to n, then norm of alpha square equal to norm alpha 1 square plus norm alpha 2 square and so on norm alpha n square. Therefore, norm of alpha square equal to inner product alpha comma alpha. So, which can be written as summation I equal to 1 to n alpha I, summation j equal to 1 to n alpha j, then you take it for both, and then we have a double summation of alpha I comma alpha j. Summing with respect to j first, and note that inner product of alpha I comma alpha j is delta ij, and these mi's are pairwise orthogonal, then norm of alpha square equal to summation of alpha I comma alpha I, which is equal to summation of norm alpha I square. So, this means norm of alpha square equal to norm of alpha 1 square plus alpha 2 square and so on, norm of alpha n square. Now, this is most important, that how to generate what vector, orthogonal vector. So, the technique is explained in Gram-Smith process. So, Gram-Smith orthogonalization process. So, carefully understand that the formula, it is derived from the statement that if that inductive definition is hard to grasp, look at the first few steps in the algorithm. The vectors W1, W2, W3 are calculated as shown. So, W1 equal to V1 by norm V1, first initially you assume it, then W2 equal to V2 minus inner product V2 W1 into W1 divided by norm of V2 minus V2 comma W1 inner product into W1. So, this technique we have to apply, so that W2 will be generated, and W3 is nothing but W3 minus, so V3 minus inner product V3 comma W1 into W1 minus associated with the W2 V3 comma W2 into W2 divided by norm of the numerator. So, this way we can generate in generalize of n vector, so that we can do that orthogonally, the orthogonal process of the n vector we can do that. So, if it is unnormalized WK introduced, then process can be described another set of equation, call it as W1 equal to V1, where W1 stands for W1 by norm of W1, W2 equal to V2 minus V2 comma W1 into W1, where W2 equal to W2 by norm of W2, and then W3 equal to V3 minus inner product V3 comma W1 into W1 minus V3 comma W2 into W2, where W3 equal to W3 by norm of W3. So, this way we can do the process of finding the the vectors W1, W2, W3. So, that is orthogonally how it is project, and orthogonally how to generalize we can do with the help of this theorem. Now, let us go with an example of the discussed statement of the theorem. Apply Gram-Smith process to the three vectors V1 equal to 103, V2 equal to 220 and V3 equal to 312 in the order given. Now, what you have to do is, first step you take W1 and V1 are same, you have to consider, and then let it be given 103. Now, first normalized vector is a technique is, rule is W1 equal to W1 by norm of W1, means that vector divided by what, a root of 1 square plus 0 square plus 3 square is equal to 1 by root 10 will come. So, for every case is 1 by root 10, 0 by root 10, 3 by root 10 will come. So, this way we can calculate W1. So, based on this technique, we have to go to the next vector, which is unnormalized form is W2 equal to V2 minus inner product V2 W1 into W1, that is V2 you know 220, and then W1 you know just you found out. So, that you have to take it, and then already W1 value also you know that. Then inner product V2 and W1 you have to do that, then simply corresponding product them, so that you can get it the value of what this, that is inner product what 220 of W1 is 1 by root 10 into 103. So, this means 1 by root 10 into 2 into 1 2 plus 2 into 0 0 0. Therefore, we have what 2 by root 10, and then the resultant easily we can calculate it corresponding the values of the vectors. and then multiply with W1. W1 is 1 by root 10 into what? 103. So, we have what? Corresponding value can be generated 2 by, that is 1 by 10 into 206, and then subtract with the V2, we have 1 by 5 into 9 comma 10 comma minus 3 will come. So, this way we can do with the help of finding the W2 in terms of the vectors V1, V2, V3. So, note that at this stage there is a vector W2 that is orthogonal to W1 by theorem. The numerical verification in this problem yields inner product W1 W2 is 1 comma 0 3 into 1 by 5 into 9 comma 10 comma minus 3. So, product them, we have the net value, say 1 into 9 by 5 plus 0 into 10 plus 3 into minus 9. So, net value is become 0. Therefore, we can calculate W1 W2 vectors. Now, normalization of the now produces norm of W2 is equal to 1 by root of 190. Therefore, W2 equal to W2 by norm of W2, which is equal to 1 by root 19 of 9 comma 10 comma minus 3. So, from this you can see that the inner product W1 W2 becomes 0. So, next we subtract from V3 its orthogonal projection onto the span of W1 W2, creating W3 equal to V3 minus of inner product V3 W1 comma W1 minus V3 W2 W2. So, V3 you know the value 312 and W1 is 9 by root 10 of 1 by root 10 into 1 comma 0 comma 3 and minus 31 by root 19 into 1 by root 19 of 9 comma 10 comma minus 3. So, already we found out all the values, simply substitute and using the inner product vector space definition. So, first term as it is, second term V3 and W1 inner product, do that, you can get the 9 by 10 into 1 comma 0 comma 3 and the V3 W2 you do that inner product, you can get the value of 31 by 190 into 9 comma 10 comma minus 3 will come. So, corresponding entry add and subtract, you can get 4 by 19 into 3 comma minus 3 comma minus 1 will come. So, this is a way we can calculate W3. So, now normalizing the product of these above ideas, and W3 norm of W3 is equal to 4 by root 19 and W3 is W3 by norm of W3, which is equal to 1 by root 19 into 3 comma minus 3 comma minus 1. So, it means the gratifying to make the few checks to see that the results are correct. For example, inner product W1 W3 you have to calculate, net value becomes 0. Also, we have to calculate W2 W3 of inner product 0. So, it means one are mutually orthogonal to one another. So, this is the verification we can do that. So, therefore, how to find out the orthogonal process of one vector to the another vector. So, this is called as Gram-Smith orthogonalization process. Suppose the vectors are not normalized, unnormalized Gram-Smith orthogonalization process, how to do that. So, the basic idea is same, but subtract from the given vector its orthogonal projection onto subspace. So, formally start with the basis V1, V2 and so on n vectors. The newly created vectors will be denoted by Z1, Z2 and so on, so that the confusion with the earlier algorithm is avoided. So, thus we define Z1 equal to V1 to start. Next, construct Z2 by subtracting from V2 its projection on Z1. So, the result is Z2 equal to V2 minus inner product V2 comma Z1 by inner product Z1 comma Z1 into Z1. So, in the next step we subtract from V3 its projections onto Z1 and Z2. Therefore, Z3 equal to V3 minus inner product V3 comma Z1 by Z1 into Z1 minus V3 comma Z2 by inner product Z2 comma Z2 into Z2. So, this way we have to find out Z3. Steps K does this, and Zk equal to, in general, Zk equal to Vk minus summation j equal to 1 to k minus 1 Vk comma Zj by inner product Zj comma Zj into Zj. So, this way we can do the unnormalized orthogonalization process of Gram-Smith algorithm. So, the main difference between the algorithm for the Wk and Zk is that the vectors Wk are normalized after each step, whereas Zk are not, hence they remain unnormalized. So, avoiding the calculation of the square roots is another advantage. Now, let us go with an example. Find an orthogonal basis for R cube by applying the unnormalized version of the Gram-Smith process to the three vectors V1 equal to 1 0 3, V2 equal to 2 2 0 and V3 equal to 3 1 2 from the previous example. Now, in step 1 we set Z1 and V1 are equal, right, 1 comma 0 comma 3. In step 2 we obtain Z2 by subtracting from V2 its orthogonal projection on Z1. So, we have Z2 equal to V2 minus inner product V2 comma Z1 by inner product Z1 in comma Z1 into Z1. So, V2 you know the value 220 minus Z1 you know the value, that is 1 by 5 into 103. Now, you have to subtract from one to another, 2 minus 1 by 5. So, it becomes 9 by 5. Next one is 2 minus 0, right, and then 0 minus of 3 by 5. So, this will get the corresponding vectors. So, 2 by 5 will come, and then we take the 1 by 5, then it becomes 10. So, center value becomes 10. Now, this calculation gives us the scalar multiplication of 9, 10 minus 3. In this version of the Gram-Smith process, we do not hesitate to use the convenient multiples of the vectors, since we seek only the originality and not the normality of the vectors. Hence, we can simply let Z2 equal to 9, 10 minus 3. In step 3, we subtract from V3 its orthogonal projection on Z1 and Z2. Therefore, Z3 equal to V3 minus inner product V3 comma Z1 by inner product Z1 into Z1 minus V3 comma Z2 divided by inner product Z2 comma Z2 into Z2. So, the value becomes V3 minus 9 by 10 into Z1 minus 31 by 190 into Z2 equal to 3 comma 1 comma 2. So, which is equal to minus 9 by 10 into 1 comma 0 comma 3 minus 31 by 190 into 9 comma 10 comma minus 3 and 1 by 190 into 120 minus 120 minus 40. So, again ignoring the scalar multiples, we get Z3 equal to minus 3 3 1. So, the skeptical reader can check the orthogonality of inner product Z1 comma Z2 equal to 0, Z1 Z3 equal to 0 and Z2 and Z3 equal to 0. So, it is easier to construct an orthogonal basis by first constructing an orthogonal basis and then normalizing the vectors all at once at the end. From the preceding work, we see that the unnormalized vectors can be Z1 equal to 1 0 3 and Z2 equal to 9 10 minus 3 and Z3 equal to minus 3 3 1. So, their norms are norm of Z2 equal to root of 1 square plus 0 square plus 3 square equal to 10 and norm of Z2 equal to root of 9 square plus 10 square plus minus 3 square, which is equal to root 190, and then norm of Z3 equal to 3 square plus 3 square plus 1 square equal to what? Root of 90. So, the normalized vectors are then Z1 equal to 1 by root 10 into 1 comma 0 comma 3, Z2 equal to 1 by root of 10 root of 90 comma 9 comma 10 comma minus 3 and Z3 equal to 1 by root 19 of minus 3 comma 3 comma 1. So, this agrees with the result in the example. That is all.